Hi everyone, welcome back. All right, let's tackle the rest of this practice exam. This is the fall 2015 practice exam. Let's do a couple more questions. How about question number 3? Let's start there. All right, this is a fill in the blanks. I try to have some version of fill in the blanks usually on my exams. And what we're doing is trying to train your brain a little bit in synthesis, trying to scramble some of those reactions. So let's follow our same process. Let's see if we can figure out what some of these reactions are, and then that's going to help us with our figuring out, what blanks to fill in, what those reagents are. So let me write them out. We've got the radical halogenation, the SNs, and the Es. Now each semester is different. Radical halogenation wasn't on this test, but it is on yours. And for this one, they had just a little bit different with one reaction with an alkene that we haven't seen yet. That'll be in our next unit. So let's go ahead and try and figure out this first one. All right, right away, leaving group. Nice and easy to spot. So that's right on our electrophile. So in this case, it's secondary. Got a nice secondary electrophile. Now, we don't actually know what our conditions are, but we have some clues in our product. We added that SH to that exact same carbon that was our electrophile and secondary. So right away, it's not a radical halogenation and it's not one of the E's. It has to be an SN. So could it be an SN1 or an SN2? Yeah, actually it could be either one. It depends, if it's primary, secondary, tertiary, but in this case it's secondary, and that works for both. So this one I would actually have to accept two different answers. I would take your version of an SN2, and that should look like this. You need that negative on your sulfur, and then some kind of solvent like DMF. That would be a good answer. I would also take the SN1. So what would the SN1 look like? The SN1 would be just nice and neutral sulfur lone pair. Okay, so I would actually accept either answer. They would both work. All right, let's take a look at the second one then. Again, leaving group right there. This time it's tertiary for our electrophile. And if we check out the product, we have a double bond. So right away that's telling me, okay, that is either an E1 or an E2. And what's going to make the difference for that? Well, let's draw them both out and let's see if they both work. So if it were an E1, let's say we took that and we treated it with something like water. Okay, which double bond would we make though? Don't you make the more stable double bond with an E1? Aha, you do, and that's not our product. So we need to cross off the E1. So that leaves an E2. Okay, but now we have some rules for E2. How do we avoid making this one the most stable double bond? It depends what base you use. We have to use a large base like LDA in order to make that product. Okay. Ooh, how about this next one? We do not have a starting material, but we have a product and we have reagents. So now we're trying to train your brain to go backwards. This is thinking about synthesis. So right away, what's your gut tell you? What kind of reaction do we have? Well, we definitely have one of the SNs, SN1 or SN2, because we did a substitution. What does this reagent tell you? Is this an SN2? Nope, this is an SN1. You've got a nice polar protic, only your solvent and your nucleophile are the same thing. So that means an SN1. And then where do we substitute? Right there. And that is tertiary. You can use bromine or chlorine. It doesn't matter. They're both going to do the same thing in that case. And do we worry about a rearrangement? No, that is on a tertiary carbon, so we're not going to rearrange. All right, let's do the same thing for this second one. All right, we've got reagents. So what do these reagents tell us? That is a strong base. So if this is our base and this is our solvent, this is a perfect recipe for an E2. It could be an SN2. How do we tell the difference between the two of these? Well, with an E2, it doesn't matter if your electrophile is primary, secondary, or tertiary. They're all going to work. But for an SN2, the only way this would be a nucleophile is if our electrophile is primary. So let's go to our electrophile, find our leaving group. Son of a motherless goat. There is no leaving group there. Aha! This deserves a sparkle pen because this is a trick question. There is no leaving group, no leaving group, no reaction. Okay? This is my favorite trick question. I've mentioned it in class. It's awesome. Okay, so let's check out this bottom one here. We've got a leaving group. We are on a primary electrophile. We've got a good nucleophile and a nice polar aprotic solvent. This screams SN2. So let's draw that product. And we substitute right where your leaving group was. Okay. Awesome. All right, so that's our fill in the blanks question. Let us cruise down. We have another predictive products question. So let's see if we can figure this one out. Sodium hydroxide and water. Again, that screams E2. That is a small base. Okay. Let's find our leaving group. And since it's an E2, we need to find any beta hydrogens. We have a beta right there. We have a beta right there. So why do we care about our size of our base? Size matters. Why does the size matter? Because our small base is going to go for the most hindered beta hydrogen. So that is this one. We're going to end up making the double bond in that most stable double bond. Okay, let me erase that. So let's see if we can figure this out. All right, we had some more rules for an E2 because, check it out, we have stereocenters. So what do you need to do for this? You need to model it because we need anti-periplanar. So how do we know if we have anti-periplanar? We need to take this, we need to model it, and we need to put it in a Newman projection. Now, I like to always put beta hydrogen and leaving group right away, anti-periplanar. That is the only way this reaction works, is if these are anti-periplanar. So then our job is to take our model set and actually put the other groups in, because as soon as you line up and have anti-periplanar, wherever your other groups end up, they will stay there. So that's what's awesome. If you build this model, you're going to find that you've got both of your methyls on the same side and your alkyne and your benzene on the same side. So as soon as you line this up, you are about to make this double bond right there. And your whole compound is frozen in space right like that. Okay, now sometimes we draw it a little bit nicer. We draw it this way. Oh, let's actually follow my drawing. All right, so that means our benzene is down here, our alkyne is down here. So then what's left? What do we call this, E or Z? Okay, we're gonna draw a little line down the middle, and we're gonna rank our groups, high and low. And then we're gonna notice that our highs are on the same side. Remember our little acronym from class, Z same side. So our product actually is going to be that Z double bond. Oh, that deserves a sparkle pen. So this is going to be our product. You can draw it either way. If you want to include the Newman projection, that's even better, but you definitely need the Newman projection in order to draw that compound. All right, I think we have time to tackle the roadmap. What? Now, you know your roadmaps will have spectra. This roadmap doesn't actually have spectra. Yours will have IR spectra, but let's tackle it anyway. All right, C7H13Br. Whew, okay, let me just draw. Let me see if we have any rings. So if I just draw C7 and add a bromine, that's one way to do it. We can also use our formula. How many hydrogens are we going to have there? 1, 2, 3, 4, 5, 6, 7, 8, 11, 12, 13, 14, 15. This would be 15. This is not it. So we definitely have a ring. Do we have more than one ring? No, because we've got 13 hydrogens. That is one ring. All right, so rings in general we can have a 3-membered ring, 4-membered ring, 5-membered ring, 6-membered ring. We can even have a 7-membered ring. Wait, is that 7? Yeah. Okay. And then we can add bromine to it. So let's look at what else is in the question. At least 3 stereocenters. So right away that crosses off this guy because you don't have something extra hanging off of there. And then let's put in our bromine, and we would need one more carbon on a 6-membered ring. The most that can really ever get us is 2 stereocenters. So actually those don't work. So what about a 5-membered ring? Well, we need to add 2 carbons to that and our bromine. Now if we spread out wisely, in theory, couldn't this give us 3 stereocenters, depending on if we've got cis or trans or how we make that happen? And we could have an optically active compound. All right, so and then it's actually giving us 2 compounds, and it's saying compound B is a diastereomer, and it is meso. All right, do you remember what meso means? So let's keep our 5-membered ring for a minute. So could we have something that's a meso? Well, what if we have exactly a nice plane of symmetry? This is what's going to give us meso. So maybe we're in business here with something like that. Let's look at the rest of our question. Compound A is reacted with base and water to give only one product, C. Let's see, what would happen if we treated that with base and water? Well, wouldn't we lose our leaving group and do an elimination reaction and end up with that? And then if you've got symmetry and your compound, it doesn't matter if you make the other one because they are the exact same thing. So what if we made this, we had that? So could they be the same thing? They could. It depends. So this is from compound B, but we reacted compound A. So what if we took this one, and if something like this was compound A, and we had a bold or a dash there, then what would we make with our treatment of base? We would make these two. What if we had, oh, that looks terrible. Hold up. Ah. Okay, what if we made this one? And then what if we had this one? Now these are the same thing. So that was a fun question. So sometimes I hate giving answers to roadmaps because you can actually have lots of different options for answers. They just have to fit what's in the question. So I hate giving my answer because sometimes that's not always the only way to think about it. What if we looked at, this one is tricky because this 5-membered ring, you also would have to really pause for a second and assign R and S to these, and then also figure out if this is even a stereocenter. So if this is meso, this isn't even a stereocenter. But, or is it? Again, you'd have to figure out R and S. R and S themselves are actually different. So if one side is R, one side is S, this is a stereocenter. So it's actually a really tricky question. So I would accept a variety of answers because I'm not sure I would expect you to know that R and S are different. And if we assign it, truly this is meso, but I think if you look at it, this is R and this is S. So that actually makes this not have 3 stereocenters because this would now not be a stereocenter. So you'd have to double check that, but I would just be super happy if you recognized any of this and you gave me any of these structures would be fun. What about a cyclopropane? Could we make that happen? Well, here's 3 carbons and we need 7. So what if we did some version of this? That might be kind of fun. I think you could do this. You'd have the similar argument to this one. You'd have symmetry there and you could put your leaving group somewhere. Could you figure out how to do that on, oh, what happened, y'all? Could you do that on here? Could you have 3 methyls and a bromine? And you had the right bolds and dashes. Ooh, that might be kind of fun, right? I think you could monkey around with that. So I just want you to recognize in your roadmap all of those issues and make sure somewhere you have some bolds and dashes because that's how you can tell your stereocenters. You can't leave it without bolds and dashes. So awesome. Well, let's stop this one for now and then we'll double check. I think I hit all the questions. There might be one synthesis left to hit and I'll put that in a second video.